Hello students, in another class of chapter number 1, that is solution. So far we have discussed the first colligative property, that is lowering in vapor pressure. This is the second and third colligative property you can see in front of you. The second colligative property is elevation in boiling point. You all know that the boiling point of pure water at 1 atmospheric pressure, it means at normal atmospheric condition, is 100 degrees Celsius. But when we add any non-volatile solute in water, in fact in any other solvent also, the boiling point definitely increase. This increase in boiling point of a liquid when we add non-volatile solute in it is known as elevation in boiling point. I repeat, change in boiling point or it is increase in boiling point of a liquid when we add non-volatile solute in it is known as elevation in boiling point. Now, why or how the non-volatile solute increase the boiling point? To understand this, look at here. First, the definition of boiling point, which you already have prepared in class 11 in states of matter. Boiling point is a temperature when the vapor pressure of a liquid becomes equal to vapor pressure of its atmosphere. So here, with the help of this diagram, I try to show you once again what is boiling point. Suppose this is the vapor pressure of a liquid, maybe water, at room temperature, and because it is for water, it means it is for solvent. I denoted vapor pressure as P naught. So P naught, it is the vapor pressure of water or pure solvent at room temperature. Once we increase temperature, the vapor pressure you can see here continuously increase. This is 1 atmosphere, which is pressure of atmosphere in normal condition. When we increase temperature, the vapor pressure continuously increase, and at this particular point you can see the vapor pressure becomes equals to atmospheric pressure. This particular temperature is known as boiling point of a liquid. Here it is boiling point of water. Now what happens when we add non-volatile solute in the solvent? You already have prepared the previous class. So when we add non-volatile solute here, the vapor pressure definitely decrease, and therefore now the vapor pressure becomes, suppose it is now vapor pressure. I repeat, when we add non-volatile solute, the vapor pressure will decrease. Let this is the vapor pressure of solution. Because we added non-volatile solute, vapor pressure has decreased. Once again, increase temperature, the vapor pressure also increase in similar ways. So you can see here, when we increase temperature, the vapor pressure increase, and now the liquid boils at this particular temperature. At this particular temperature, T B dash. Look at here, when you added non-volatile solute, the vapor pressure has decreased, and because vapor pressure has decreased, the boiling point has increased. Now this is a 100%, this is always 100% chance that whenever we add non-volatile solute, the vapor pressure definitely decrease, and because vapor pressure decrease, the boiling point will definitely increase. This increase in boiling point is known as elevation in boiling point, and it is represented by delta TB. Delta means it is change, but here rather than it is change, we can say it is elevation, because the boiling point definitely always increase in this situation. Now this is from Raoult's law. Delta T, which is lowering in vapor pressure, is directly proportional to mole fraction of solute. You already prepared it. So this is from Raoult's law, and the second equation is from graph. You can see in this curve. In this curve, this change in vapor pressure is directly proportional to change in temperature, or lowering in vapor pressure is directly proportional to elevation in boiling point. Further, if you add some more amount of solute, vapor pressure further decrease, and because vapor pressure further decrease, its boiling point will further increase. So here this you can get from the curve, and this is from Raoult's law. When you equalize these two equations, when you use these two equations, you can get this delta TB directly proportional to XB. These two are directly proportional to each other. Now delta TB equals to KXB, where K is constant, which is also known as elevation constant. Further, for numericals, xb can be written as nb upon nb plus na. Nb is solute, this is solute, and this is solvent. We all know that moles of solute is negligible as compared to moles of solvent. So here you can neglect this quantity. I repeat, why we neglected it, because it is solute particles, and the moles of solute is negligible as compared to moles of solvent particle. So here I neglected it, and Na, it is moles of solvent. Moles of solvent can be written as, it is mass of solvent upon gram molar mass of solvent. Now here, if you read these two quantities together, it is mole of solute divided by mass of solvent, and this is a concentration term which is known as molality. So here in place of this two you can write small m, that is molality. Now this is a constant K, this is also a constant, it is gram molecular mass of solvent. Now, gram molecular mass of solvent is always constant for a particular solvent. Like if it is water, then it is always 18, and similarly, if it is benzene, it is always 78. So this is constant, this is constant. The product of these two numbers is also constant, which is given as Kb. K is known as elevation constant, Kb is known as molal elevation constant. So finally, you have to use this formula for numerical purpose. Delta Tb, which is elevation in boiling point, equals to Kb into m, where Kb is molal elevation constant, m stands for molality. You can also write the same formula in this format also. It is Tb dash. Tb dash means it is boiling point of, solution. Tb, it is boiling point of solvent. This is constant. It is mass of solute, gram molecular mass of solute, and this is mass of solvent. When we use mass of solvent in gram, definitely here you have to write 1000 as per the formula of molarity. So comparatively a small colligative property for us as compared to lowering in vapor pressure. So you will have numerical on the base of this formula, and you can use the same formula in this format also. Now the third colligative property, this is depression in freezing point. Once again, freezing point, if I ask you what is freezing point of water, then answer is 0 degrees Celsius. It is the freezing point of water. But how can we define freezing point? There are two possible ways to define the freezing point. The first is, it is a temperature at which both solid and liquid states coexist. Another way, which is more important for us here, how can we define freezing point? Once again, we will use help of this curve to define freezing point. Let this is the vapor pressure of, once again, a pure solvent like water. So it is vapor pressure of water in liquid state at room temperature, and let this is a vapor pressure curve for solvent in its solid state. Solid state means if it is for water, then this is the curve for ice. Elevation in boiling point, during the boiling point we have increased temperature, and because we increase temperature the vapor pressure continuously increased. Here to find out depression in freezing point, to define freezing point, we will decrease we decrease temperature, and once we decrease temperature, the vapor pressure also decrease like this, and as soon as when we decrease temperature the vapor pressure decreases. The temperature at which the vapor pressure of solvent becomes equals to vapor pressure of its solid state, this particular temperature is considered as freezing point. I repeat, this was for liquid, this was for solid. When we decrease temperature, vapor pressure decreases, and when the vapor pressure of liquid becomes equals to vapor pressure of its solid state, this particular temperature is known as freezing point. Now what is depression in freezing point? Once again we will add some amount of non-volatile solute in the pure solvent, it means in water. When you add non-volatile solute, vapor pressure decreases here, let this is the vapor pressure of solution now having non-volatile solute. Decrease temperature, vapor pressure decreases like this, and now it freezes at this particular temperature. I mark this temperature as TF dash. So look at here, this was the freezing point of pure water, and this is freezing point of solution having non-volatile solute. Because vapor pressure decreases here, the freezing point also decreases. This is known as depression in freezing point. Now once again you can see here delta P directly proportional to XV, it is as per Raoult's law. And once again from the curve you can see change in vapor pressure is directly proportional to change in temperature. It means the the lowering in vapor pressure is directly proportional to depression in freezing point. So delta P directly proportional to delta TF. This you can get from the curve. This is from Raoult's law. Equalize both of these two equations. Then once again you will get delta TF directly proportional to XV. Delta TF equals to KXV. If you look at here, then you can see here this formula and this formula both are same formula. The only difference is F, and there we had B for boiling and F for freezing. K is known as depression constant. Now you can do similar calculation here also, and finally you will get similar formula delta TF equal to KF into M, where KF is also known as molar depression constant, also known as cryoscopic constant. So these two formula are 100% identical. Delta TF equal to KFM and delta TF equal to KF into M. Only difference is delta TB was TB dash minus TB. It means it was solution minus solvent. But here it is solvent minus solution, because the freezing point of solution is less. So we first write freezing point of solvent minus freezing point of solution. So both are similar formula, easy to remember. Generally derivations are not part of the question paper, so you have to remember only the final formula for numericals. There are few common applications of depression in freezing point in day-to-day life. Especially three applications you have to remember. First, you may ask why sodium chloride or any other salt poured over snow after snowfall. The answer will be sodium chloride or salt. They act as non-volatile solute. They will decrease freezing point of snow, and therefore the snow can easily melt. It flows and it helps in clearing the roads. Similarly, another possible question, why ethylene glycol, which is also known as coolant, why ethylene glycol is added in water? I hope you remember coolant. It is used in radiator of vehicles, and this help to cool down the engine. During winter, the water can be frozen out, and therefore it cannot act as coolant. Therefore, some amount of ethylene glycol, which is here non-volatile solute, added in water so that its freezing point decrease, and now water will not get freeze at 0 degree Celsius. It may freeze at minus 5 degree, minus 10 degree, minus 15 degree, depending on the amount of ethylene glycol. It means non-volatile solute added to the water. So these are few applications which are common for depression in freezing point.